millions of people, globally dealing with things like ALS or stroke,
Yeah.
and they just lose the ability to communicate.
Right. The thoughts are there, the intent is clear, but the physical path for speech is it's blocked or damaged.
Exactly. And that's where brain-computer interfaces, BCIs, come in, this sort of frontier tech offering, well, incredible hope, really, trying to bypass those damaged pathways.
Letting the brain talk directly, essentially.
Yeah.
And when we think about accessing those brain signals without surgery, non-invasively, EEG is usually the go-to starting point.
Electroencephalography,
Yeah.
the electrodes on the scalp thing.
Yeah, exactly. And the big plus for EEG is how accessible it is. It's portable, it's relatively low cost, certainly compared to invasive methods, and crucially, it has amazing temporal resolution.
Meaning it's fast.
Super fast. It catches brain activity changing millisecond by millisecond. For something like thinking or planning speeds, which happens so quickly, that's, theoretically ideal. It feels like something that could actually be usable for you, potentially.
Okay, that sounds fantastic. But there's always a but, isn't there? The catch with EEG.
Well, yeah, it's kind of a double-edged sword. While it's great at telling you when something happens,
It's not so good at where. Port spatial resolution, is that it?
precisely, hard to pinpoint the exact source, but maybe even more critical is the signal itself. It's incredibly faint, just this tiny electrical whisper from neurons firing.
And that whisper gets drowned out.
Completely. Buried under the brain's own background chatter. And worse, just overwhelmed by massive electrical noise from, like, blinking your eyes, clenching your jaw,
Muscle
movements.
Artifacts, right? Those are way louder than the actual brain signal you want.
Orders of magnitude louder, yeah. That noise, that's the core problem. Trying to pull out a meaningful signal related to speech from that messy, low-level EEG data, that's where you need something powerful.
And that's where the AI comes in. Deep learning.
Absolutely indispensable. You need these sophisticated AI tools, like deep learning models, to basically sift through all that static and somehow find the subtle pattern that actually means something, that represents intended communication.
Okay. So the mission for this deep dive then is figuring out how AI is actually doing that.
Yeah.
How it's trying to decode speech language directly from these really noisy, complex EEG signals.
And the progress, honestly, it's pretty remarkable when you look at where things were just a few years ago. We've moved way beyond just, classifying a handful of preset words.
Which is the really goal. Right.
Right. Now AI systems are starting to generate continuous streams of text or even synthesize audio that you can actually understand as speech, all from non-invasive EEG.
Yeah, I saw some really striking examples in the research, like one system working with imagined speech, just thinking the words, synthesized Chinese words, and human listeners got it right over 91% of the time on average. It's kind of incredible.
It really is. And then there was another one for silent reading, using EEG to generate text, achieving a BLEU1 score around 40%.
Okay, explain BLEU1 quickly.
It's basically a measure of how much the generated text overlaps with the real text someone was reading. 40% might not sound perfect.
No, but going from, like, nothing to 40% accuracy on actual text from brain signals, that feels like a huge leap. It shows the AI is starting to get the structure.
It represents a really significant milestone, getting that kind of intelligibility or text quality from such noisy signals.
Yeah.
But digging into how they got those results also highlights the biggest challenge right now.
Which is the fact that these amazing results often come from really specific, constrained setups, like needing tons of data from just one person.
You hit the nail on the head, exactly. One study, yeah, great accuracy on over 500 phrases, but it needed something like 175 hours of data from one participant.
Wow.
So the massive bottleneck for actually getting this out of the lab and into the real world is, one, the lack of big, diverse data sets, and maybe even harder, dealing with intersubject variability.
Intersubject variability,
Go ask.
meaning my brain is different from your brain.
Pretty much, yeah. Everyone's brain structure is slightly different. The patterns of activity for the same thought can differ. Even the skull thickness changes the signal quality. So a model trained for hours and hours on my EEG
Might totally fail on mine.
without a whole new lengthy calibration process just for you, that's the tricky part for making this practical and widespread. And it's a fascinating AI challenge, too.
And on top of that, there are still practical things like needing faster systems for real-time chat
Right.
and better hardware, right?
Yeah,
Comfortable stuff you could actually wear, like dry electrodes without the goop.
definitely. And, as we get better and better at decoding more complex stuff, intentions, thoughts, maybe even inner speech, it inevitably brings up some really big ethical questions.
Yeah, that's kind of the elephant in the room, isn't it?
Yeah.
What does it mean for, like, mental privacy if AI can start interpreting signals straight from your brain?
That's the crucial question, isn't it? The one this progress really forces us all to think about. And it's something important for you to consider as this technology moves forward. How do we balance this amazing potential benefit with the need to protect, well, what's inside our own heads?